Hello, everyone. Welcome to our final talk of the GOCC this semester. It'll be given by Travis Grigsby on pattern avoidance and fiber bundle structure on Schubert varieties. But before I throw it to Travis, I wanted to remind everyone of our community statement. The GOCC is for graduate students by graduate students, and as such, we think it's important that we all remember a few key things. First, we are all learning. Second, everyone has something to contribute. And finally, no one has all the answers. And that means you as the audience, us as the host, and also the speakers. So if you have any questions, feel free to put them in the chat or to address them directly. If you put them in the chat, we'll make sure the speaker can see them. But yeah, with all of that in mind, take it away, Travis.
Okay, thank you, Mark and Sarah and organizers for giving me this opportunity to speak about something that I know and like, which is combinatorics. And specifically, I've been studying the question of how do pattern avoidance conditions affect the fiber bundle structure of projection maps. And projection maps from Schubert varieties. And so that's what I'm going to talk to you about. And I just want to say that Schubert varieties are pretty cool. They're really awesome. They arise in the context of intersection questions. So, you know, you have this classical question of how many lines intersect four given lines in three-dimensional space. And it turns out that the cohomology classes of Schubert varieties, you can multiply them together and you can answer this type of question. And just in general, when you're looking at Schubert varieties, there's a beautiful interplay between the combinatorics of their indexing permutation and the geometry of those Schubert varieties. So the dimension of the Schubert variety can be calculated through the length of the permutation. Whether or not the Schubert variety is smooth can be described by the indexing permutation avoiding different patterns. And the topological structure of a Schubert variety is CW complex and is described by taking the union over an interval in the Bruhat partial order placed on the permutation group. And so there's a whole lot of stuff that is captured by the indexing permutations, a whole lot of geometry that's captured, and the rank matrix, the descent sets, things like that. We'll also have geometric interpretation. And so I want to talk to you about a lot of these ideas, and then the research question that I've been looking at. Okay, so this is what we'll focus on, a projection from, pi here is the projection map, and it's projecting onto the Grassmannian. The Grassmannian is just the collection of R-dimensional subspaces of Cn. So you pick an N and an R, and you're looking at subspaces of that Cn of that dimension R. And so I'm going to assume nothing. And so I'm going to, because this is the type of talk that I would have wanted, where like everything is sort of like spelled out. But I may go through things a little bit fast. So if anyone has questions, please put them in the chat. I'm sort of flying blind, and Mark's gonna like let me know and read off those questions. Okay, so the background setting for this is flag varieties. Schubert varieties are a subset of the full flag variety. So I should tell you what flags are. So a flag is a sequence of nested subspaces of Cn, so that the dimension of the ith space in the sequence is I. So for example, this is the second space in the sequence. It should have dimension 2, and so on. And we're going to fix a basis. I'm calling that basis E1 through En. It's just you can choose the standard basis where there's a 1 in the ith coordinate of your vector and zeros everywhere else. And you can form a flag by taking successive spans of these basis vectors. So if you just look at the span of the first vector, that's a one-dimensional space. The span of the first two vectors, two-dimensional space, and so on. And if you start in the ordering that you described on your basis, and you go from smallest to largest, taking these successive spans, we call that the standard flag. In contrast, if you go in the reverse ordering, starting at the last vector, and then taking successive spans, so the last vector, the last two vectors, and so on, that's called the opposite flag. So those two flags are useful. They meet transversely, and because of that, they'll help us later define some a nice intersection variety. Okay, so another way that I'll write them just for shorthand is if you ever see me write just E, that's going to be shorthand for the standard flag. If you see an E bar, that's going to be the opposite flag. And that's just the same two flags that I mentioned a second ago. So the full flag variety is just going to be the collection of all possible flags that you can have. And let's just get right into it. A Schubert variety has the following definition. You look at all the flags, and given a specific permutation, you can write down that permutation's rank matrix. And membership in the Schubert variety is determined by intersection conditions of a flag with the standard flag, the components of the standard flag. And they basically have to respect this rank matrix condition, which looks really abstract, but we'll do an example here in a bit. So I'm going to tell you about the pieces that go into creating this variety. And one other thing, the open Schubert cell. So I should go back. This is, the closure of Schubert cell. So it has greater than or equal to symbol. That's how we'll distinguish it. And if you just have an equal to symbol, that's going to be, an open subset, an open cell. Okay, so let's go to the next one. So what's a permutation? So I said index and permutation. So here's the one-line notation. Remember, a permutation is just a map. So this is the map that sends 1 to 3, 2 to 5, 3 to 1, 4 to 2, and 5 to 4. And in one-line notation, you just keep that ordering and write them from left to right. And that describes the same map. Given a permutation and its one-line form, there are many different ways you can describe permutations. You can describe them as grids of dots, as matrices, and there are many different ways to write the same permutation. I'm going to take the convention that you just measure down a column, and if you have, say, a number in a specific entry, so in the ith or the jth space, then you go to the jth column and you put a dot in that row. So I put a dot in the third row of the first column. If I go to the second entry, I put a dot in the fifth row of the second column, and so on. And this is called the Roth diagram for this permutation. And you can read off lots of statistics from this Roth diagram about that permutation. In particular, you can read off the rank matrix. So how do you get that rank matrix? You're going to take northwestern rectangles. So suppose I wanted to know what entry goes in this cell of the rank matrix. That entry defines a corner, and then I take the northwestern corner or the northwestern rectangle, and I just count the number of dots I see in that rectangle. So since I see one dot there, I put a 1 in this entry of the rank matrix. So let's do another one. So if I want to know what goes in this entry of the rank matrix, again, draw the northwestern rectangle using that as my corner, my bottom corner. I see that there are 2 dots, so I'll put a 2 in that entry, the rank matrix. And you can fill out an entire array using this method, and that will give you the rank matrix of that permutation. Okay. So if we have that rank matrix, then we can more explicitly say what membership means for flags in the Schubert variety. And there's going to be, like, say, if you just look at this, we're in a 5-dimensional space. There are just so many possible dimension conditions that we would have to check. You know, potentially say like 25 conditions. If you're just saying that each one of these entries gives you a condition. And so there's a lot of, there turns out to be a lot of redundancy, and you can remove that redundancy by the following procedure. Go to each of the dots in your Roth diagram and shade the column below and including that dot. So starting from that dot, shade below it. And then starting at each dot, shade to their left as well. And you can see you have these voided regions, this white space. And in that white space, you look at the southwestern corners of those void regions. And just to their left, they identify the most essential conditions that you need to describe membership in the Schubert variety. So, you know, here's the southwestern corner, and to its left, there is going to correspond a condition for membership in the Schubert variety that's just absolutely essential. And these will be the only ones that you need, sort of like a minimal set to describe membership in that variety. Okay, and so how to read off the dimension conditions. I like to put the standard flags components on the left and a flag's components at the top. And then so I look at this condition here, and it says that the first component of the standard flag and the third component of your flag you're testing for membership, they have to meet in at least 1 dimension. And so that's why there's a 1 here, and these are the components being considered. And you do that for each of the other 2 as well. Sometimes you can simplify those conditions, and instead of writing them as you know, just an intersection condition, you can also write it as a containment condition. I usually like to do that. So for instance, E1 is a 1-dimensional space. So if it meets V3 in at least 1 dimension, then it means it's contained in V3, and the others are similar to that. And so another way to write this Schubert variety more explicitly is like this. And so this is what the Schubert variety say is. This is
A
how
quick
it works.
question, Travis.
Yeah. Yes.
Can you always write these intersection conditions as containment conditions?
No.
Okay.
No, for the
Seemed
small
optimistic.
cases. Yeah, no. A lot of times you just have this dimension is bigger than whatever floating around. So it's not always as cool looking as this. Cool. All right. So there's geometry associated to this Schubert variety that you can read off from different facts about the permutation. So I wanted to go through one of those. The dimension can be read off by calculating the length of the permutation. The length of the permutation winds up also being equal to the number of inversions that the permutation has. And it's easy to see from the Roth diagram again, how many inversions your permutation has, actually just what the inversions are explicitly. But one way you can do it is you go to a dot and you draw the northeastern rectangle, and you count how many dots are in that rectangle. That's the number of inversions related to, say, for example, a 5 in this case, the number 5. And so there are 3 dots there. So there are 3 inversions. And if you do that for each of these dots, you can get a count, and that will count the inversions for each dot. You add them up and you get the number of inversions, which is the length, which is very nicely the dimension of this Schubert variety.
We have a question in the chat.
Yes.
From Andrew, which says, are Schubert varieties degeneracy loci? Like, are these matrices coming from some map between vector bundles?
The way I've seen it, Bolton has a bunch of notes all about, and the degeneracy loci I've always seen indexed by the partitions, and there is a relationship between those partitions and the Schubert varieties. I can't really remember what that relationship is, but I know they're related to each other.
Awesome. Thank you so much.
Okay. Okay. So you might be, so like I said, I'm assuming nothing, even though I wrote it as the dimension as the number of inversions. I'm also assuming that maybe you don't know that. And I'll need this later on because I'll just be talking about inversions constantly. So what's an inversion? Well, the natural way to order numbers is 1, 2, 3, 4, 5, so on. So if you saw a list of numbers that was 1, 3, 2, 4, 5, you would say that 3 and 2 are out of order. They're inverted from the way they should be. And that's basically what an inversion is. So given a permutation, an ordered pair is an inversion if the number is bigger. So if A is bigger than B, but you see A to the left of B or preceding B. So for example, in 2, 4, 1, 3, I see a 2 before this 1. That's not supposed to happen. 1 comes before 2. So 2, 1 is an inversion. And you can get the other inversions similarly. And those 3 will be all the inversions for that permutation. The length of the permutation is denoted by LW, and it's just the sum of, or it's just the total number of inversions. And so there are 3 inversions here, so this permutation has length 3. The length also corresponds to, when you thought as reflection groups, the length corresponds to the smallest word describing W in terms of simple reflections. So that there's that relationship as well that I won't talk about. So some extreme examples of Schubert varieties. There turns out to be a permutation of a unique permutation of maximal length. I'm going to denote that by W naught. And it's just you write all the numbers backwards in one line notation. So for S4, that's 4, 3, 2, 1. It sort of has the maximal number of inversions, which means it has the largest length as well. The identity is in the exact other extreme. That's when you write all the numbers in the correct order, and you have the least number of inversions. It has length 0, and there's a unique minimal length element like that as well. So the Schubert variety for the longest word, the longest element, is actually the full flag variety. And the Schubert variety for the smallest element, the identity, is just the singleton set. So there's, I know I have set brackets and everything here. There are no conditions, or there are no extra conditions for membership. That's literally the only point in that Schubert variety. And here, whoops, here, there are no conditions for membership in that Schubert variety as well. All flags are allowed. Okay. Okay, so something that'll come up later, that I'll need later, is to describe the Bruhat order. I mentioned earlier that the topology of the Schubert variety can be described using the Bruhat order, and so we should know what that is. So if you have a transposition, it's just a 2-cycle, and it's just when you swap two numbers in the one-line notation. So for example, 2, 3 means that I'm going to swap the second and third entry of the one-line notation of this permutation. And so 2, 3 is the transposition. And when you apply it to this permutation, this is what you get. So that's what a transposition is. And in Bruhat order, you can say that a permutation U is less than a permutation W if either U equals W, or more interestingly, if there's a sequence of transpositions that bring you from U to W such that you go up in length every time. So as long as you can do that, then that means you have that comparison in the Bruhat order. So for example, we can take 2, 4, 3, 1 to 2, 4, 1, 3 using that transposition, but the length of 2, 4, 1, 3 is 3, and the previous length is 4, so we actually went down in length, and so we don't have 2, 4, 3, 1 as being less than or equal to 2, 4, 1, 3. I have therefore because you would somehow have to have checked all ways of going between those two. But because this is, so this is why my little guy is sweating, but because that's the only way you could have transposed and gone from those two permutations, that's exhaustive. But if you can find one sequence of transpositions that does it for you, then you can say that you have the inequality in Bruhat order. And so here's a way to go from 1, 2, 4, 3 to 2, 4, 1, 3 using transpositions. The length goes up every time, and therefore you can conclude that 1, 2, 4, 3 is less than 2, 4, 1, 3 in the Bruhat order. So it's a CW complex. The Schubert variety is a CW complex, and you look at the open cells. So that's, whoops, that's the equality condition in the way in the set that I described earlier. This is a disjoint union because it's a CW complex. And if you're unfamiliar with them, just remember that this is just like triangulating a a manifold, but instead of using simplicial complexes, we're using spheres. Okay, so how does an interval in the Bruhat order look? It sort of looks like this. And each one of the permutations in this interval, for each one of them, you'll have a corresponding open Schubert cell. So, rank matrix and membership condition where there's equality. Okay, so finally, we make it to the projection maps. So the projection maps are really nice. They just forget most of the information about the flag. So if you go from the flag variety to the Grassmannian, you have different components for that flag, for any flag that you have in the flag variety. You're trying to go to the R-dimensional spaces, so you just remember the R-dimensional component of that flag. So that's the projection map. And the question that I'm curious about is, when is the Rth projection map a fiber bundle? And you can just think of a fiber bundle as putting a local product structure on the thing you're projecting from. And by that, I mean, not this map exactly, but when this map is restricted to Schubert varieties or intersections of Schubert varieties. And so there's actually an answer to this. This projection map is a fiber bundle if and only if this indexing permutation avoids these split patterns. So there's a pattern avoidance criteria that's required and describes this. And there are other ways to describe it as well, but I'm going to focus on pattern avoidance. So what's a pattern? A pattern is just a permutation, and you sort of forget about the numbers of that permutation and you just pay attention to the relative order. So maybe ignore that, and let's just do an example. So here I have the permutation W, and it contains the pattern 312. And why does it contain the pattern 312? Well, the relative order of 312 is you have a large number, then a small number, then some number in between them. And that's exactly what you see here with 6. It's the largest, 3, that's the smallest, 5, that's a number between the two. And so W contains numbers in that relative order, and so it contains the pattern 312. There's another example of containing 312. So you really don't have to have exactly those numbers, although of course, the way it's written, W also explicitly has the permutation U in it as well. You can see this visually looking at the Roth diagram. So the relative order is really easy to see. You just have a dot, you go up, and then you go down. And so if you can do that, then you sort of contain that pattern. If you don't contain the pattern, if you don't contain that permutation in a relative way at all, then we say that you avoid that permutation. So the pattern 1, 2, 3 is a sequence of 3 descending dots. They don't have to be on a diagonal like that, but you just need to, from left to right, see 3 dots descending. And you can see very clearly from the Roth diagram of W that that doesn't happen. Therefore, W avoids that pattern. A split permutation is really hard to, it's tedious to write down the definition. So that one's also best done by example. But in short, it's just going to be you contain the pattern in the way I just described, but there's this division bar that you have to respect. And so if you have part of your pattern on one side of the division bar and part on the other side, you sort of have to respect that for W to contain that pattern. So here's an example. Does W 6-3 split 1542? Does it contain 3 split 1-2? And the answer is yes. Here's an example of that. So I have the whoops, I have the 3 on the left. That's the largest number. And then the smallest and then the middle number are on the right. And so that's an example of that containment. That's another way that it's contained. But it's location dependent, as in location where you draw the division bar dependent. And so I've drawn the division bar in the third location now for W. So it's technically a different split permutation. And you can see that, for example, I don't see the smallest dot and then descending down like this. I would have to see 2 consecutive or 2 descending dots on the right-hand side of the division bar, and all of the dots on the right-hand side are increasing, for example. And so I don't contain the split pattern 3 split 1 2 relative to that third position for W. So that's how split pattern avoidance works. And I think maybe there is a typo. That typo, it should say avoids.
Can I ask a clarifying question?
Yes.
So you're saying, I think you said this, but just to make sure, if a permutation avoids like the split condition, it has to work for all of the bars, like it has to avoid it for any choice of bars? Or do you specify?
Okay, I see. You specify the bar first.
Okay.
And then you ask, do you contain the pattern relative to that choice?
Okay,
And then
so it's
every
not
time
like
you
for all
redraw
the
the
bars.
bar. No. If you
Okay.
avoid it for all the bars, then you avoid it in the original pattern avoidance criteria.
Okay.
But yeah.
Okay, thank you.
And just to further clarify this, because I have a way of wording this in my mind, and I think it's equivalent, but I'm not sure. Well, split pattern avoidance, like you split patterns avoid other split patterns. You don't have permutations avoid split patterns, because as you noted, if there isn't a sense of that, and if it does it for everything, then it's just standard pattern avoidance. Okay.
Yeah, so yeah, that's right. I think I understood you right. Yeah, split permutations avoid split patterns. We're not asking like, does a split permutation avoid a pattern in the traditional sense? Is that good, Mike?
Yep, that's great.
Okay, awesome. Okay, so maybe now this answer to this question has slightly more meaning, and that we understand all the working parts. So the projection map has, is a fiber bundle if and only if the indexing permutation avoids those split patterns. And so now we have more of a sense of what that means. Okay, so let's do an example. So here is the permutation 1 4 2 3. We saw how to write the rank matrix. We saw how to find the essential conditions. And so there's a description of the Schubert variety for 1 4 2 3. And you can write it more nicely as E1, explicitly showing that E1 has to be the first component. And you can even write the third component as a sum of 2 spaces, given that you know that the second standard space has to be contained in your third component. So anyways, so if you do that, then it's just that second space plus a line in C4. Okay. I want to project from this. So I would want to project from this. So notice that we have the pattern 3 split 1 2 at the second position. And so if I use the second projection map, then I will not have a fiber bundle. And so let's verify that. So the space E1, E3 happens to be in the image of this projection map. And if you take the pre-image of that space, you get this. Okay, that's a singleton set. It's just that one flag. If you take the pre-image of E2, so the span of E1 and E2, then what actually happens is that sort of gives you some freedom. So for example, let's go back up to this first one. The condition is that you have to, the third component has to contain E2. So if you already contain E1 and E3, the only way you can also contain the space E2 is if you add the second standard basis vector. The moment you do that, now you have completely determined U. And so this winds up being the only flag that projects down onto E1, E3. However, if you say project onto E2, well, then containment of E2 is almost guaranteed for your third vector space components or flag components. And so you have the freedom of choosing U. You have the freedom of adding some linear space to that. And so you have one dimension of freedom. Since those two fibers have a different dimension, one's 0-dimensional, the other is 1-dimensional, then they can't be fiber, this map can't be a fiber bundle, because one of the properties is that all the fibers above points are homeomorphic, and so they should also be equidimensional, and these are not. Okay, so this map failed to be a fiber bundle, and that is because the indexing permutation contained the pattern 3 split 1 2. So one of the things you can do is you might be curious, this is combinatorics, so you might be curious as to how many permutations in SN avoid those two split patterns. There's this summation formula. These symbols here are just the following factorial. And so this is how that formula looks. It's there's a more symmetric way that you can write this, but I haven't seen a way to say like factor this into a product or anything like that. But it would be nice to know if there's a nicer way that this to saying that the largest number, say n, has to be to the left of your division bar, and you want to count the number of permutations that avoid these patterns, but also have n on the left of the division bar. Then you can also find formulas, and you can also find generating functions for those. So not you can find recursive formulas, and you can also find generating functions for those numbers as well. So it's another cool sequence.
A quick question. So KL and R are permutation or split permutations of what length? Like how in what symmetric group?
Oh, in SN. Sorry. The N is the N tells you the group as well.
Oh, n is literally the number n, not
N is
n
literally the
elements
number
before the dividing line. Okay.
Oh, okay. Sorry. No, yeah, no, this is in SN. So the so let me go back. So if you're looking for permutations in SN, that's the same N.
Okay.
Yeah. Okay.
I guess I can save it for the question period. Carry on.
Okay. Okay. So, okay, so we've got 3, 1, 2, and 2, 3, 1 as being the conditions that tell you when these maps are nice. But why? You know, some people would be happy with just this pattern avoidance criteria, but maybe there's a geometric explanation. And you know, it turns out that when you're looking at the fiber bundle structure of these projection maps, in the Schubert variety case, you only have to check the T-fix points. The T-fix points are just going to be those that are permutations of like rearrangements of the basis vectors. And then you take spans, successive spans as in the same way that you did for the standard flag and the opposite flag. So those will be the T-fix points when you project down onto those components. But there's an alternate description that you can think of all of this. So this is slightly theoretical. I'm going to race through because the interesting stuff is later. So you can think of this as, you can think of the flag variety as the matrix group mod the Borel subgroup, where the Borel subgroup that I'm looking at is the upper triangular matrices. And each matrix in GLN is a flag. Basically describes a point in the flag variety, a single flag. So it's the coset that describes that's a flag. And anytime you have a permutation, you have a permutation matrix. So the way I'm writing this permutation matrix is the same way that I wrote the Roth diagram. Just now, instead of dots, I'm placing ones, and in all of the empty cells, I'm placing zeros. And so that's how you get the permutation matrix. But if you have the permutation matrix, you'll wind up being able to write explicitly how the variety looks. So it turns out that the flag variety can be decomposed into this disjoint union. This is, again, just the Bruhat decomposition that I mentioned before, maybe thought about with the Schubert variety for the longest word, the longest element. And each one of these is going to be an open cell. It's going to be the open cell associated to the permutation W. Okay, you can explicitly write how that cell looks if you write the permutation matrix. Okay, similar to the way you do the Roth diagram. And then above the ones, you want to put free variables. So I have asterisks here describing free variables. And so maybe there was an asterisk there, but if you think about the right cosets by upper triangular matrices, you're allowed to do column elimination. And so this pivot here will be able to cancel out whatever entry was there. And so you wind up getting a 0 there. You can always make it to a matrix that looks of this form. There isn't really freedom there. Okay. So if you fill out your matrix in this way, first put in that permutation and then these asterisks, then you have the open Schubert cell. Okay, it's a 3-dimensional space because there are 3 asterisks, 3 free variables there. One of the things that I wanted to point out, if you're looking at this diagram, is that there's a 4 here. So if you go to the column for 4, so the second column, but where the number 4 appears in the one-line notation, and you look at the asterisk in the 3rd row and the 1st row, that's corresponding to the fact that 4, 3 and 4, 1 are inversions for that permutation. And you have 2, 1 and there's in the column for 2, or where 2 appears, there's an inversion in the first row. That's identifying that there's an inversion. Sorry, there's an asterisk in the first row. That's identifying that there's an inversion with 2, 1. Okay, and so if you look at the Schubert variety, so before I had a little circle, circle above this, so it was the open cell, but now I'm taking the closure down in Bruhat order, and you're going to get everything in that interval below 2, 4, 1, 3 in the Bruhat order, and they're each going to have some sort of matrix that looks like that. And so you can just write this all out. There are too many there for me to have gotten on one slide, otherwise I would have. But you can explicitly see how this variety looks. Okay, so let's run through another example. So looking at 2, 4, 1, 3, I'm going to project onto E1, E2, E4. This is just project. If you look at the initial part of that permutation, that's defining the space that I'm projecting onto. So it has a 2, a 4, and a 1, so I'm going to project onto the space spanned by the first, second, and a fourth basis vectors. And so you can see from the interval, from the Bruhat interval, exactly which permutation cells are going to project onto this point. And how do you do it? You just look at their initial pieces. So those are the ones that are going to do that. So if I take the pre-image, I want to know what cells from the entire Schubert variety captured by that interval project onto that point. I can identify them. And for each one of them, I can explicitly write how that cell looks. Okay. The thing that I need to make sure of is that the spans will give me the span of E1, E2, and E4. So here's a description of that one. And I guess what I was trying to say is, notice that here for this cell, these cells correspond to each other, by the way. But in that cell that I have the asterisk highlighted, correspondingly, I have a 0 there, and the question is why? And it's because if I actually gave myself the freedom to choose an arbitrary input there, then that would actually sort of mess up getting the span of these vectors, because I'd have some, some non-trivial component in the direction of the third basis vector. And to avoid that, I can make that 0. Then this matrices of that form are still in the collection of matrices of the form on the right. So I'm still in that cell, but that what I have on the left is explicitly how the pre-image looks. Okay. So if you actually just write out the dimension, if you actually just write out the pre-image, then you can see the dimension is 2. You just look at all the dimensions of the cells in the pre-image, and you look for the one that has the largest dimension. The top dimension is going to be the dimension of the pre-image. So, so the top dimension is 2 in this case. And so the pre-image of that fiber is, or the dimension of that fiber is 2. Okay, there's another way that we could have done this. So you could just write out what the Schubert variety is, all of its conditions, take the pre-image and calculate it more explicitly. So this is sort of I'm looking at the time. And did we start late, Mark? Like, do I have a little bit of time after 1?
So we'd like time for questions. We started about 3 minutes after 12.
Correct. Okay. So, okay. Thank you. So maybe let me get to some other stuff, but you can calculate it explicitly as well. And once you've identified, say, so let me just go through what this slide is saying. So say I'm taking the pre-image of this space. That means I've fixed the third component. And you want to see what are all the V1s and V2s that could go along. And here for V1, you're basically choosing any line from two-dimensional space. So that's 1 degree of freedom, 1 dimension of freedom. And for V2, you're going to be able to determine it once you've determined V1 by just taking something that's in the complement, orthogonal complement of V1, and but that is also in V3. Okay, so V1 is a 1-dimensional space, orthogonal complement is 2-dimensional. So again, you're choosing a line, a direction from a 2-dimensional space. You have a 1 dimension of freedom, and so in total, you have 2 dimensions of freedom there. And so that fiber has dimension 2. Okay, so that can get tedious. And so, we try to look for ways that can make these sort of arduous processes less painful. And so for permutation, you can associate a diagram of lattice paths that records the rank matrix. So this is my attempt at making things a little bit easier. The way you do it is each path in your diagram is going to be determined as they start at the bottom left-hand corner of some grid. The ith path is going to have I steps. You can let them coincide with one another. They have to take a north step whenever their predecessor takes a north step. And you can't let them dip below one another, but that sort of happens from what I just said. And then also, I'm not allowing consecutive north steps. So again, maybe an example. So here is the permutation 5, 1, 2, 4, 6, 2. I've drawn a path. I'm going to draw a path by saying that the first path takes its north step. So if you think about the rules that I just described, each path winds up being determined by a unique north step that is not forced upon it. So a unique unforced north step. So remember, they have to take a step whenever their predecessor does. So if they take a step of their own volition, that sort of defines who they are. And so the red path is going to take its unique north step at the 5th location. And then I'm going to draw, say, the second path. And the way I'm going to do it is, well, there's a 1 here. So at the first location, the blue path is going to take its north step. And then it can only take 2 north steps. So it's now going to take a north step when it's forced to, which is when its predecessor took a north step. So it goes up like that. The pink path is forced to step up at the first location because the blue path did. And then it takes its unique step at the 3rd location. So there it is. And as I continue over here, it's forced to take another step where the blue path took a step. And now it's taken 3 steps. So that's the end of the pink path. And so each of the paths are drawn like that. Okay. So because this diagram, it comes from the rank matrix, you can see the inversions. So for instance, they're going to be north steps above a path's unique north step. So there's the inversion 5-1, and you can see it's made with the red and the blue path. And that inversion is seen explicitly as the blue path being strictly above the red path, where the red path took its north step. And so the red and pink also have the same phenomena going on. And there's also an inversion corresponding to the numbers associated to those paths as well. And you can continue to see these inversions all over the diagram. These paths are in correspondence with the permutations, so they're going to inherit the Bruhat partial order. And projection, in the same way I'm projecting from the Schubert varieties, corresponds to just fixing one of the paths. So if I fixed the green path, what I'll wind up doing is saying that I have to take, I have to have a path, and it has to take a step at the first location, the third location, the fourth location, and the fifth location. So that path is fixed in the diagram, and it's going to take steps at those locations. And there will be a bunch of other diagrams that have that path, but are, say, in the interval of consideration in Bruhat order. So I don't want to really describe that too much. But you'll get that path, and you can look at the inversions. So these are all the inversions in this diagram. I showed a lot of them in yellow earlier, and I've just decided to circle only the feet of those north steps. Some of these are inversions absolutely just have to be there because the fixed green path forces that to happen. I've called those frozen vertexes. And if I look at the vertexes that are not frozen, those will count the dimension of the pre-image of projecting onto, say, the point corresponding to that path. In this case, the point E1, E3, E4, E5, the span of that space, or those vectors. Okay. So I just label that with, the symbol script L. And so here's an example that we've been going through. So I could fix the green path. That's going to be the same as projecting on E1, E2, E4. I can look at all the inversions in the diagram. I can ignore the ones that are forced by the green path. And I see that there are two unfrozen vertexes. And that's going to make the dimension of that fiber 2 as well. Also notice that we're ignoring 4-3. So if you remember, there's that asterisk in the top cell, and I highlighted it, and then I said it wound up being 0 so that the span is correct. That corresponds to what's going on right here and why we have this frozen vertex. So that asterisk is like the frozen vertex.
So we are running past
so we're out
the
of time.
hour. If you want to,
okay,
if you want to hit any other highlights, now's the time. But otherwise, I'm going to throw it open to questions.
Okay. So the idea is ultimately I want to project from Richardson varieties, which are intersections of two generic intersections of Schubert varieties. And I want a way of describing all of that. And so you can show with those lattice path diagrams, you can show that the only way you can go up in dimension on the fibers is exactly when you've, say, taken a pattern that had 3, 1, 2, and you switch the 1 and the 3. It's easy to see from the lattice diagrams where it might not be easier in another way. Or if you had the pattern 2, 3, 1, and you switched again the 1 and the 3 to get a 2, 1 split 3. And so because of that, that gives me a conjecture on maybe what I have to do to ensure that projecting from a Richardson variety or intersection of those two is a fiber bundle. What you want to do is sort of make sure that you don't contain any T-fixed points where they would produce one of those situations. Namely, you have a 3, 1, 2 for one of the T-fixed points and a 1, 3, 2 for the other. That's the intuitive idea. And so, yeah, that's where I'm presently at.
Okay, let's thank our speaker. Oh, there's a lot there. We're going to keep the recording going for the initial round of questions. Depending on people's various schedules, it's okay if you have to duck out now. But if you have any questions for Travis, go ahead.
Also, I still can't see right now because if somebody had a question about a slide, I want to be able to go back to it. So if somebody has a question in the chat, could you read it for me?
Absolutely.
So I do have a question. So you mentioned this nice way to get the number of essential conditions, this
Yeah.
shadow region. This seems to be a nice statistic. Do you know more about it?
It's called Fulton's essential set. I'm not
So the
the
statistic
only
number of essential conditions. How is it distributed?
Oh, like of the number of conditions. No, I don't know any, say, like general facts about how many essential conditions you'll have.
Okay. Yeah. Thank you.
I just don't know.
Yeah. That's okay. Thank you.
But it would be cool to know.
I remembered my question because I was not good and didn't write it down. So you mentioned that there was a specific way of counting split permutations, which had in the left box, which I'm sure there's a reason why you would care about that. But so split permutations, there's what, 2 to the n minus 1 n factorial of them in Sn? Because you can put not 2 to the n minus 1 times Sn, because you only have one split. Like you write a permutation, then you put a bar in somewhere.
Mm-hmm. Right, exactly. So you said there are n minus 1 times n factorial.
Okay, and I just realized that I misread this theorem initially, and I now have answered my own question. It was, what about, if I only put the bar in the first 3 spots? Well, that's just changing my indexing on R here.
Yeah, exactly. So
okay.
you pick where, so this is just counting once you've fixed where you're going to draw the division bar, how many permutations avoid these patterns with respect to that choice. It's kind of by this formula.
Okay, excellent.
Yeah. But you could just sum over R.
Sure.
I have just a really quick, kind of related question from earlier. So with Richardson varieties, are they also defined kind of similarly using like a rank matrix being greater than or equal to, like a rank being greater than or equal to or less than or equal to some number?
Yes, that is true. And in fact, I was going to do an example where we were doing exactly that. And so you'd have your essential conditions, and you just need the flags to satisfy both of them. The thing that's different is that when you go to write down your essential conditions, you're gonna, one of these permutations is shifted. So I should say the way to define the Richardson variety would be to have 2 Schubert varieties, and then one of them, to make the intersection generic, you'll want to shift by the longest element. And so you can think about multiplying those Schubert cells by that matrix. And when you do that, you can go through the derivation of what that variety is like normal, but you are looking at intersections with the opposite flag for that shifted variety. And but the conditions that you get are the same. And so you'll be able to describe your Schubert variety by these containments in this case. It's gonna like cut out some possibilities as you would expect. And so in this particular case, you wind up being forced to fix V3, where before V3 had, for 213, V3 had some freedom. And so you'll wind up losing that, but they're constructed in a similar way.
Interesting. Awesome. Thank you. An amazing talk, by the way.
Awesome. Thanks. Oh, good.
One quick question from this thing you just mentioned about Richardson varieties. You said you have to, multiply by the opposite permutation. Would that mean a Richardson variety of a cell with itself is not just itself? Like you don't, if I choose U for U and V, I don't just get back XU?
I'm trying to, Mark, that's an interesting question. I don't really know. I had some slides right after my thank you slide. So here's an example in S3 of the full flag variety. And this is that matrix description of those cells that I mentioned before. And so for this Schubert variety, it's that union of cells on the left. And the sort of the shifted version is on the right. The thing that happened is that, I changed the way that I took a cell like this and I just flipped it vertically like that. And so you can see that the asterisks now appear at the bottom. So that's what happens when you multiply by the longest word element given this model of these varieties. And so what you're going to do, say like with this one here, if I can write it, is let's just see what happens. You have a 1 star star, and then you have a 0 0 1, and then you have a 0 1 0. And here, for example, with your first dimensional V1, so like your flags are going to be successive spans of these columns. For the first one, they actually just have to coincide with one another. So your first vector is going to have some non-zero component here in the first entry, maybe some other non-zero component in the third entry. And then this one in the middle can be variable. And then when you go to get your second flag, there would be more that you would have to try to do. You would have to look at the span of these first two and see if there is some way that you can reconcile their span. And so you might end up with something more interesting than just that T-fix point that you mentioned. And it's kind of a challenge to do because you can't just say like intersect the columns. You have to like see what the spans are, and there will be like ring conditions that you have to check and stuff. So it can be done. I've done like a lot of the examples in S3 and S4 by hand. I've got like code that I'm writing to do it more generically, but it's just a hard problem sort of describing what those varieties look like. I don't know the actual answer to your question, Mark, except to say that maybe you can get something more complicated than just say the one T-fix point that's determined by the permutation.
Okay. That's excellent. I think I'm going to end the recording here.